Today I'm going to talk about unikernels and how we are using them to optimize the cloud workloads at the Genezio. But first of all, I want to set up some expectations. So this is really a research track for us at Genezio. We are also building a commercial product that helps developers deploy their application, and that's the main thing for us. And this today is basically research that we've done to try to improve resources and cost for us on our own infrastructure. So this talk itself, it will be a talk about challenges and bumps that we've tackled alongside this, this journey, let's say. And second of all, what I really want to know, what I really want to do here is kind of sparking your curiosity. So how many of you actually heard about unikernels? Oh, that's great. That's great. We have a knowledgeable audience. That's really nice. For the others, I really hope that you will learn something today, that we will learn something new. And I want to really bring up the focus on unikernels because I really believe that this is a great piece of technology, and it can optimize the way that we are running apps in cloud instances. So that being said, let's start the presentation. First of all, we have a vision at Genezio. So we want to optimize resource allocation. That means less costs and less resources used. We want to make an easy-to-use and secure cloud platform. We truly believe that the developer should focus on writing code, not really on deploying, managing instances, and trying to bring back lost instances. And we want to focus on fast response times for the calls, because no one really wants to build a web app or a mobile app that doesn't respond in an instance that's unresponsive, right? So let's introduce unikernels by doing a comparison to what we already know about how to launch things, how to launch applications in VMs. So first of all, we have the classic virtual machine. This is a very highly isolated thing. So we have, first of all, the hardware. We have a hypervisor that's starting kernels. And we have the good old kernel, Linux kernel there, and our apps. We have user space, kernel space, and multiple processes. And this is a really beefy thing that we have to run. It takes a lot of time to boot up. And it also takes a lot of resources. The next best things are containers and Docker stuff. So as we can see, we don't have the hypervisor level anymore. We have just the hardware, and on top of it is a kernel that is shared for all the apps, let's say. This is not really that isolated, but it's more lightweight, so we can boot it up more fastly. So this is why we're using containers, because they are kind of lightweight. And the next best thing that takes best of the both worlds is unikernels. So we see that we kept the hardware and the hypervisor because we want perfect isolation, but we have a much smaller kernel, and on top of this kernel is the app. What is really specific about unikernels is that the source code of the app is bundled together with the kernel, and it's run as a single process. So basically, we don't have system calls anymore. We don't have user kernel space. Everything is running in kernel space. And we also can build a more specialized kernel. So for example, if your application is just about compute and computing stuff, and it's not using the TCP stack, you can not build the TCP stack into the kernel. So basically, we have a much smaller attack surface that makes it more secure. We still have the isolation that we saw at VMs level. And we have a more lightweight thing, like in containers. And that gives us speed, and that gives us security and isolation. OK. So I talked about unikernels, and I introduced the thing. So now let's see how we tick all the boxes at Genezio that we want to build a secure platform, we want to make it less costly, and we want to have faster response times. So we actually build a kind of an orchestrator that is going to spawn the VMs that are containing unikernels in a serverless or function as a service approach. So what is actually happening is that when a request is coming to our web app, Firecracker and the unikernel is going to boot up. with a small Genezio wrapper and the user app on top of it. So basically, each time a request is coming, we are going to boot up this thing, and we are going to process the response, give back the response to the user, and then essentially in a few minutes, this VM is going to scale down to 0. This way, we don't use any resources if any requests are not coming to the web app. How many of you know what is Firecracker? Because I'm going to... Great. OK, I'm going to... This presentation has a lot of concepts, so I'm going to bring them on the table, and I'm going to ask you if you know them in order to bring some context. So Firecracker is a very lightweight virtualizer that we can use to spawn the unikernel on top of it. Anyway, so requests keep coming, so we keep spawning the VMs and process the responses and give back the response to the user. This comes with a unique set of challenges. So first of all, we want to reduce the call starts. This is the time when no VM is present, no VM is booted. So when a request is coming, we have to actually boot the unikernel, we have to start the process of the app, and so on. And that takes time. So we don't want to have a penalty for the user on that. We want to reduce that as much as possible. We want to optimize the unikernel image upgrade, because when we are going to host many unikernel images with a lot of users and a lot of apps, we don't want to redeploy each unikernel image for them. And we also want security and process isolation on the long run, because we don't want a web application to be able to access resources from another web application. OK, so let's see how we are tackling reducing call starts. We are leveraging here good old snapshots. You probably heard of it, or you have a hint of what that is. So before any request comes in our cloud infrastructure, we are actually booting a unikernel image. We are loading Node.js for Node.js apps. We are loading this process, and then we create a snapshot here. This is basically a picture, if you want, of the state of the VM right now. And we are putting this picture away because we are going to use it in the moment when a new request is coming. So when a new request is coming, we start Firecracker that is going to help us load the snapshot that we've previously put it away. And we are going to attach the user code to this in order to process the request. And also, we are going to import the node, to mount the disk and import the node process. And from this moment, now on top of the unikernel, the user app is going to run and is going to process the request. Another way to reduce even more the call starts is to have a wormed pool of VMs that are waiting requests. So basically, we have some number of VMs that are just booted up and waiting in a pause mode. And when an incoming request hits the server, we are going to put the user code on top and give back the response. If we have 100 such of VMs in a worm state, and we have 101 requests, the last request is going to fall back to the snapshot thing that we already did. So basically, this is just the best scenario case that you are hitting a warm VM. The worst scenario case is when you are hitting a cold one and you have to get a snapshot from the storage. OK, so we also want to upgrade the unikernel image. What that means, unikernels are also evolving, and they are launching and releasing new versions. So once a new version is released, we actually want to push this unikernel image to each of the instances that we are running on the cloud. So we want to do this in a way that we don't have to redeploy the application, because I told you that the user code is kind of embedded into the unikernel image. So what we actually did is that we are mounting the user code as a separate disk. So we can mount it and unmount it as we want. So the unikernel image is going to be kind of a base image. And when a user is coming up, this base image is going to be put together with the user code. That means that when a new unikernel is released, we can just update the base image. So this is what I've just told you about the rebuilding. OK, and we also want security and isolation. That's kind of a given, because we are using Firecracker Jailer to run each of the unikernels sandboxed, which means that we have separate process namespaces, separate network namespaces, and so on. And we also, using Jailer, we can also remit resources for VMs, such CPUs and I/O throughput, because we don't really want one web app to starve the other apps. Okay, so now I kind of talked about concepts and what we are actually doing, but let's see numbers, right? Let's see that we've actually managed to increase, to be fast and to be fast, essentially. So what we're actually going to see is a round-trip time benchmark. That means that in this setup, we have a client that is going to send requests to our infrastructure, and is also going to send requests to an AWS Lambda server, because we want to compare them. So what we actually compare here is AWS Lambda, which is very similar to what we are doing here. We also have Genezio over Unikernels. So we have an web app over Unikernels, and also have a web app over Linux. So I'm going to measure here is that the time that a request makes from the client to these servers and back. So, and that also includes the TLS encryption and decryption. So it's over HTTPS. Just keep that in mind. So we have a simple hello world example that we're going to run. It's essentially a ping pong. So I'm going to send a request, and a hello string is going to come back, and I'm going to measure the time. The letters here are a bit small, but I'm going to walk you through the graph. So this is a cold call. That means that no VMs are spawned on the cloud side. So when the request is hitting the cloud, it's going to boot the unikernel and the kernel first, and then handle the response. So essentially what is happening is that AWS Lambda, the round-trip time for AWS Lambda is 300 milliseconds, and it's the orange one. And Genezio over Unikernels and Genezio over Linux, the purple and the blue one, are around 70 milliseconds. So this is a huge improvement in the round-trip time. And for the warm call, obviously, because we have instances that are already spawned on the cloud, the round-trip time globally is less. So for AWS Lambda, we have 60 milliseconds, the round-trip time. And for Genezio Unikernel and Linux, we have around 30 milliseconds. So what is interesting to see in these two graphs is that both unikernels and kernels are kind of the same for the round-trip time. So we can see that essentially it's almost the same. So why use unikernels at all? So the thing is that we are also optimizing resources. So for the unikernel version, we have less memory used, we have less storage used, just because the base image is much smaller than the kernel, Linux classic kernel storage. So we are actually using less resources to essentially have the same response time. What we want to do next is testing with different unikernels. What I didn't told you is that right now we have this proof of concept over one unikernel, which is OSV. And we also want to have a drop-in solution when you can bring any unikernel out there and put it and run it on our cloud. And we also want to add support for more programming languages. Right now we have Node.js and Go, but essentially we want to be a general cloud solution. So run everything that you are running right now on your backend. I have, I think, a lot of time for questions, so fire up.
Yes, thank you. I just want to understand how in the unikernel space, the sharing of the persistent storage works when they are completely in different kernels and they are not sharing the same I/O.
So can you go again? So
how do the applications share the persistent storage when the applications are in separate kernels?
So are you talking about the user code thing when we are mounting another thing? Because storage is kind of, the persistent storage for unikernels is kind of, you just bring your own storage, if I'm understanding correctly.
Yes, on the hardware level, yes. But when they share the same story, the two applications, when they want to
Yeah.
write on the same block,
Yes.
they go to the kernel APIs. So how the two different applications which are running in two different kernels can access the same block storage?
So I believe this is a high-level thing that you should, I guess, create some kind of a layer to communicate with the block storage. So we are kind of doing that internally, for example, but we have a layer that enables the two web apps to communicate to the shared block. So it's not really something. I don't believe that is something that is at kernel level. You can look at the unikernel being a blob of something, and if you want to communicate with other APIs and services, you kind of have to do that via network.
Hello, thank you for the presentation. I have a question. You said you can put in Unikernel TCP or whatever you want. How you determine that, and what if you have to add something new on demand? What happens at that point?
So as far as I know, you are doing that. You kind of have either to know what you need to build in the unikernel itself. So you kind of have to have some knowledge about that. Or you can use some kind of SDK such as Unicraft's SDK to actually be very simple to run in run a different kernel and build stuff into the unikernel itself. And the on-demand thing, I believe that you have to rebuild the base image if you want new stuff on it.
Okay. Yeah, so I know very well I'm from the Unicraft project. It's the other unikernel that Andrea knows
Sure.
about. I'm going to first answer the question because I got your question. We were just last week, we were trying to create a setup where we have Nginx and PHP FPM running together, and we did bump into the problem of having to share a disk for both. The approach there is actually to use the VMM. So Firecracker or anything like that is going to use probably something like Vert.io, and then via that you would have the same block device, the same emulated block device shared to both. We didn't go into that yet, but we're going to do it because it's going to be required for this. So particular use case for WordPress, we need to have an Nginx microservice. We need to have a PHP FM1 that share the same disk. So this reliance is not going to be, as Andrea mentioned, on the kernel. It's going to be on the outside world. So the VMM itself is going to provide the interface via which you are going to be able from two unikernel instances to use the same disk. That's how it's going to work. And then the question I have, because we are also considering the idea, and lovely the part with the snapshot, and I think that's going to be a major improvement, is the way I see it, and correct me if I'm wrong, you're going to have some sort of preset unikernels, meaning this is the one with JavaScript, one with Go, one with something else.
Yep.
Because if you're going to go kind of in a different area, I mean, if you're going to, let's say, support 2,000 apps, each of them is going to have their own snapshot, right?
Yep.
So is this by design you're relying on your subset of kernel that you're going to create snapshots for just to, let's say, release the burden of storing too many snapshots?
So basically, we don't have to have snapshots for each application. We have to have snapshots for each backend, for each programming language, if you want.
Yeah, but
so,
for example, if I would want to run Nginx, that would be Nginx. If I would want to run another web server, something else altogether. So is your approach only focusing on these languages, and that's why you're going to have a reduced number of snapshot instances rather than run different applications, for example?
Yeah, sure. So our infrastructure is kind of opinionated to the Genezio product itself. So you really can't, in this paradigm, you really can't run Nginx. You are going to run Genezio code if you want, which is an RPC thing. So for us, it's going to be to have to support and have base images just for strictly programming languages like Go, Node.js, and so on. So we don't really have this burden, I think, up until now.
Okay, and just one final question.
Yeah.
Even if you're going to run Node, for example, there are multiple libraries. So, for example, my application may require, I don't know Node that well.
Sure.
Library 1, L2, and 3.
Sure.
Another application is going to require 3 other libraries. Are you going to create a preset images with all those libraries bundled together?
No, so what we actually have to build is the Node.js runtime. So basically we are kind of tied to the Node.js version, let's say. The libraries and everything that you bundle comes with the user code and comes up with the mounted disk that you want. Exactly. So it's on a secondary file system. So you can actually do everything that you want. All the libraries that you need for the application is going to be externally on another disk.
Hi, great work. So I want to
Thanks.
focus a bit on the scalability of this solution. I understand that it's experimental. If I understood correctly, you basically install in an empty VM, you install the unikernel.
Yeah, okay. Yes,
The VM
exactly.
is the unikernel, right? But you still have the overhead of emulating the hardware there. So how will this scale? You have the hardware emulation for the VM itself.
So why do you say hardware emulation? Basically, we have the hardware itself. So the solution is over bare metal and KVM. So basically, we are running KVM. On top of it is a firecracker. And this is the lying foundation. And everything is orchestrated from here. So we spawn VMs, which are actually the unikernels.
Right, but you say VM, that's the virtual machine. So you still have some components that are virtualized there by the hypervisor, by Firecracker.
Okay.
Right, and you then have unikernel, which is instead of running a normal Linux kernel there.
Okay. So what exactly is the problem
So
here?
yeah, I was wondering how the comparison. It's very easy to make a comparison with containers when you have the same kernel running like 60 containers, and you can scale like that. With unikernels, with a unikernel, from what I understand, you always have to run a VM. So it's one unikernel per VM. Is that correct?
So it's one unikernel per process, let's say. It's
Per
one
process.
unikernel per process. So once you want to start a new process and a new application, you actually have to start a new unikernel. So the scalability means basically starting up multiple unikernels, right?
So you start multiple unikernels inside of an AWS Firecracker VM.
We are actually running on bare metals. This is what
You run on bare metal. Okay.
Yeah.
A VM is a unikernel.
Right.
Yes.
Yeah.
They're not running one into the other.
So if we want to make the comparison to physical hardware, if I want to run a unikernel on hardware, can I run multiple instances of a unikernel on a physical, I don't know, on my laptop, for example, or on a PC or something like that?
Yes, on top of the hypervisor, so you kind of can strictly communicate to KVM and run multiple unikernels on your laptop. So
Okay.
to test stuff, actually, I run things on my laptop.
Okay. Maybe we can take this offline after the meeting.
Sure,
Yeah,
of course.
thanks.
Any more questions? Oh.
Thank you. Maybe it's a stupid question, but do you use Kubernetes at all?
No, no
Okay.
Kubernetes at all.
Thank you.
At least not yet.
Thank you.
Thank you very much.